So we're in section 12.2, and we're going to talk about chords and arcs. Let's put the electronics away, please. Pencil, paper. So first thing we need to know is, what is a chord? We're going to talk about this new part of a circle. So what is a chord? So let's figure out what we mean when we say a chord. We'll draw a picture. A chord is just a segment with its endpoints on the circle. So I'm going to say this is A and B. So segment AB is a chord. The endpoints are on the circle. And I'm going to draw a couple of other pieces that we're going to associate with this chord. I'm going to draw this angle from the center. So that's the first piece. We call angle, and we'll put the center at O, angle AOB. Do you remember what we call the angle in the circle with the vertex at the center? What is it? Central, the vertex at the center, central angle. So angle AOB is the central angle for chord AB. So we can draw a central angle to the endpoints, and we're going to associate that angle with the chord. And then we're going to talk about this arc, arc AB. Remember, our symbol for arc is a little arc above our letters. Arc AB is the arc for chord AB. So we have a chord, we have a central angle, and we have an arc. They're all associated. They're all kind of together. And what we want to do for this first part is talk about how the chords, the angles, and the arcs are related to each other. So questions on what a chord is? Okay. So let's talk about how the chords, how the angle, the central angle, and the arcs are related. We know a little bit about this already, but we're going to talk about comparing them. So angles and arcs, what we'll talk about first. And in all of these theorems that we talk about today, we're talking about in a circle. So I'm not going to keep writing in a circle. All of these we're talking about in a circle. And we could also say we're not just necessarily inside one circle. We could be comparing congruent circles. So I'm not going to write that every time. So we're in a circle, or we could be comparing congruent circles. So for our first theorem, we're going to say that congruent central angles have congruent arcs. And the converse is also true. So we just turn it around. Congruent arcs have congruent central angles. And our picture for this, we'll draw a picture. What we're saying is, if we have a circle like so, and we have our central angle, here's our center, there are two central angles, and I'll call this O, A, B, C, and D. We're saying that if angle AOB is congruent to angle DOC, then arc AB is congruent to arc CD. And we can say it the other way around. If AB is congruent to CD, arc CD, then our angle is congruent to angle DOC. All right, so what this is telling us is that if the angles are congruent, then the arcs are congruent. If the arcs are congruent, then the angles are congruent. The angles and the arcs are related. They're the same. Angles are the same, the arcs are the same. The arcs are the same, the angles are the same. But we will also want to talk about how the chords and the angles are related. We're going to put our chords in with our angles and figure out how those are related. So let's talk about the chords and the angles. Same relationship. If the angles are congruent, the chords are congruent. If the chords are congruent, the angles are congruent. So I'm going to say congruent central angles have congruent chords. And congruent chords have congruent central angles. So the converse is true. So our picture here looks like the other one, except we have our chords. We have our chords in there. So here are my central angles. And we have center at O, A and B, C and D. And let's draw in our chords. So our chords connect these pieces here. And we're saying if our angles are congruent, so if angle AOB is congruent to angle DOC, DOC, then our chords are congruent. Segment AB, chord AB, is congruent to chord DC. So, the first part? Yeah. And I think in the classes group, which is the very first one. Oh, yeah. And then we can say this in the other way around as well. If the chords are congruent, if AB, chord AB, is congruent to chord CD, then our angles are congruent. Angle AOB is congruent to angle DOC. For the chords, if the angles are congruent, the arcs are congruent. If the angles are congruent, then the chords are congruent. same relationship, and we can say it in both ways. And now we want to talk about the chords and the arcs. So we related the chords and the angles, the chords and or the angles and the angles and the arcs. Now we want to relate the chords and the arcs. Let's talk about how the chords and the arcs are related. Same relationship. The chords are congruent, the arcs are congruent, the arcs are congruent, the chords are congruent. So we're going to say congruent chords have congruent arcs. And we can say the converse, the other way around, works as well. Congruent arcs have congruent chords. And our picture, we're just going to draw our chords in. So here are our chords on this circle. And we're going to say that if our chords are congruent, if chord AB is congruent to chord CD, then our arcs are congruent. Then arc AB is congruent to arc CD. And we can say it the other way around. The arcs are congruent, then the chords are congruent. And before we do an example, I just wanted to point out the way that we can prove all of these theorems is we draw radii from the center to connect these chords. We use the idea that the radii are congruent to show that these two triangles that we get when we draw in our radii, the two triangles are congruent, and then corresponding parts of the triangles have to be congruent if the triangles are congruent. So all of these theorems that we talk about come from drawing in triangles, drawing in radii, and showing that these two triangles that we have here are congruent. Same thing back here. We would draw in our chords and show that the triangles are congruent, so that all the parts have to be congruent. And if the central angles are congruent, then our arcs have to be congruent. So all of these theorems that we've talked about come from showing that triangles are congruent. So we turn our circle problems into triangle problems. So questions before we do an example. So let's look, I just want to draw a picture, and we want to see what all the things we can figure out from the information that we have. So here's our example. And we're going to, here's our center of our circle, and draw in some diameters. And some chords. And I'm going to say that this is D, C, A, and B. And this is point O. And we're going to say that AB is congruent to segment DC. So these chords are congruent. So let's mark that. We know those are congruent. And I'm going to say, what else do we know? So what else can we figure out if we know those chords are congruent? Arc DC and arc AB are congruent. DC is congruent to arc AB. If the chords are congruent, then the arcs are congruent. So we can mark those. I'll mark those with 3 blues there. Chords are congruent, arcs are congruent. What else can we figure out is congruent? Talked about 3 things. What's that? Angles. We can figure out the angles are congruent, the central angles. So angle DOC is congruent to angle AOB. The central angles are congruent, so I'll mark those in green. You know those are congruent. So we knew the chords are congruent, so now we've been able to figure out that all these different things are congruent. One other thing in our circle that we can figure out that's congruent. This is the center of the circle. All these radii are congruent. So we could say segment OD, segment OC, segment OA, segment OB. They're all radii. They're all congruent. I'm not going to write them all out, but we know that all radii are congruent. So from the picture we can figure out that all of those segments are congruent. So a lot of information. A lot of information in this one picture. All right, questions on the example? Okay. Let's talk about how the chords are related to their distance from the center of the circles. So chords, and I'm going to say and centers. And for this one, we're going to say chords equidistant from the center are congruent. And we can say the converse as well. If chords are congruent, they are equidistant from the center. And before we draw our picture, equidistant, what do we mean by equidistant? Same distance. Equidistant means same distance. So our picture for this, we have two chords, and they're the same distance from the center. So here are my two chords. Here's my center of my circle. We find the distance from a point to a segment or a line by drawing the perpendicular segment. So those are 90-degree angles. So we know that these segments are congruent. They're equidistant. So let's call this point C, D, A, and B. And I'll call this point E, point F, and point O. So if the chords are equidistant from the center, so we're saying if OE equals OF, then the chords are congruent. CD is congruent to AB. And we can say it the other way around. If CD is congruent to segment AB, then these distances are the same. OE equals OF. So if our chords are the same distance from the center, they're the same length. All right, questions there? Let's take a look at an example using this idea. So here is our picture. And here's our chord. One chord here, One chord there. Our center. And we know that those are 90-degree angles, and that's 7, and that's 7, and that's 12 units from there to there. And that's X, and this is 6. And we want to find X. So we look at this picture, and I say, the first thing that I see is we have a perpendicular segment from the center to my chord, and they're both the same length. That tells me that the chords are the same distance from the center. So what does that tell us about the chords? They're congruent. They have to be the same length. If this one is 12, this one has to be 12 units long. So what does that mean? Make X. X has to equal 6. The chords are congruent. Because they are the same distance from the center of the circle. So that one was pretty easy. Questions on that example? All right, last idea that we need to talk about for today is how the chords are related to diameters, chords and diameters, or chords and radii. Kind of a lot of information, but it's really only a couple of big ideas. Big ideas so far are that the chords, the arcs, and the central angles are all related. And then our next big idea had to do with our distance from the center. But the main idea, the second part of the main idea has to do with these chords and diameters. And I'm going to say diameter / radii. So in any of these theorems that we write up next, we could replace diameter with radius, and we would get the same thing. We could say diameter or radius. So the first theorem is if a diameter is perpendicular to a chord, it bisects it. So bisects the chord and its arc. And we can say the converse of this. If the chord bisects, or if the diameter bisects a chord, then it is perpendicular to it. So our picture here is we have a chord. So here's our chord. And we have a diameter or a radius. So here's my center of my circle. My diameter or my radius is going to bisect the chord. So these two are going to be congruent. And it's perpendicular to the chord. So I'm going to call this A, B, C, and D. and this point E. So if our diameter is perpendicular to the chord, so if AB is perpendicular to CD, then CE is congruent to ED. We cut this chord in half, and arc CB is congruent to arc BD. So these two arcs are congruent. And then if we say it the other way around, if CE is congruent to ED, then AB is perpendicular to CD. So diameters cut chords in half and make 90-degree angles with our chords. Or if our diameter makes a 90-degree angle with a chord, it cuts it in half. If it cuts it in half, it makes a 90-degree angle. And the other way that we can say this, it's really saying the same thing, is that if we have a perpendicular bisector of a chord, is a radius or a diameter. And the radius and diameter, the other thing we can figure out from that is our radius and diameter always go through the center. So if we have a perpendicular bisector to a chord, that guarantees us that that segment, whatever it is a radius or a diameter and goes through the center of the circle. The question's in. All right, I want to take a look at a couple of examples that use this idea of the chord and the diameter and this idea of a perpendicular bisector. So here's our picture for this example. We have a chord, like so. We have our center here. And this is a 90-degree angle. That's 3, that's R, and we know that this whole chord is 14 units. And we want to find R. So looking at this picture, what are we going to want? What do we want to try to use here? Since we have a right triangle, we want to try to use the Pythagorean theorem. Well, we need to find R. We know this side. We need to know this other side of the triangle. How can we figure that out? Well, let me draw this. Let me draw in a diameter. There's a diameter that goes through the center of the circle. And it goes right through that segment. What is the diameter? What angle is the diameter making with this chord? 90 degrees. What does that tell us it does to the chord? It bisects the chord. So if the entire chord is 14 units long, how long is this piece? 7. So this piece has to be 7 because its diameter is perpendicular to the chord, it's bisecting. Well, now we can use the Pythagorean theorem. We have r squared, that's the hypotenuse, equals 3 squared plus 7 squared. So r squared equals 9 plus 49. R squared, 9 and 49 is 58. Take the square root of both sides. and R equals 7.6. So we were able to figure out that this chord was bisected because this is a piece of the diameter. Questions on that example? Okay, let's look at one last example. Similar kind of setup, not exactly the same though. So here's our chord, here's my center. I'm going to call this Y. And I'm going to draw in this piece and say this is 15. This is a 90-degree angle, and we know that this is 11. And we want to find Y. Well, this looks kind of like the last problem. Sort of. What can we do to help us out with this problem? This 90-degree angle says, well, I would like to be able to use the Pythagorean theorem. We know that this is a piece of the diameter, so if this is 11, how big is this side? 11, those have to be the same. Because this is a piece of diameter, it bisects this, so each of those pieces is the same. I need a triangle to use a Pythagorean theorem if I'm going to use this 90-degree angle. What would be a nice way to draw a triangle? Connect with a radius. So I'm going to draw another radius. Here's another radius from the center to the end of the chord. We know that all the radii are congruent, so that radius is 15. That's 15, that's 15. So we drew in another radius in a helpful place, and now we can use a Pythagorean theorem. We can say y squared plus 11 squared equals 15 squared. So y squared plus 121. 15 squared is 225. Subtract 121. Y squared equals 104. Take the square root. And y equals 10.2. So for this problem, we had to draw in another radius, and then we could use a Pythagorean theorem. We also used the idea that this segment, the chord, was bisected by the diameter. I could have drawn my radius in over here as well, and use a triangle on this side. Either way. All right, questions on that example? All right, so our big ideas here. Chords, angles, and arcs are related. The chords are congruent, angles and arcs are congruent, and we can turn that around however we like. And we know that diameters, if they're perpendicular to chords, they bisect them. They bisect the chords that are perpendicular. And chords that are the same distance from the center are congruent. We've talked about several ways that we can compare chords and angles and arcs. All right, homework. All right, there we go.